All right, then let's get started. On behalf of my co-author, I will be presenting our work titled Learning and Co-evolving Robots in Competitive Multi-Agent Environments. The theme of this study is evolutionary robots in multi-agent environments. This research field attempts to optimize robots through evolution, like how actual organism evolves. In evolutionary robotics, robot optimization is regarded as a co-optimization problem of both robot and body and controller. Through repeated cycles of selection, reduction, and learning, both elements are optimized simultaneously. This methodology is inspired by biological evolution, where bodies are optimized through natural selection and self-reproduction, where behaviors are optimized through learning in order to adapt to the environment. Let's begin this presentation by looking back at the history of this research field. The idea of robot evolution was first introduced by Sims in 1994. Sims represented both the robot's body and controller as direct graphs and applied genetic algorithms to evolve robots to adapt to a given environment. This approach successfully evolved robots in simulation. Sims studied not only a single agent environment, such as walking, swimming, or following a pointer, but also a competitive multi-agent environment where two robots compete to retrieve a box. Since then, two major shifts have been introduced in evolutionary robotics, enabling the optimization of robots with increasingly complex behaviors. The first is the utilization of soft materials. Inspired by biological morphology, this innovation allows the creation of bodies with greater adaptability to their environments. The second is the incorporation of reinforcement learning into the control optimization process. With this, robots became capable of handling not only simple tasks such as walking, but also more challenging tasks such as object transportation or wall climbing. However, these modern approaches in evolutionary robotics have focused exclusively on single-agent robots and have yet to be applied to the evolution of multi-agent robots. In this work, we revisit the challenge of optimizing multi-agent robots through evolution for the first time since Sims' 1994 study. In doing so, our objective is to apply modern approaches in evolutionary robotics, namely the use of soft materials and reinforcement learning to multi-agent problem settings as well. Specifically, we propose an optimization algorithm for competitive multi-agent robots and develop a benchmark environments to evaluate it. Moreover, through an ablation study, we demonstrate that competitive interactions among robots have a significant impact on their evolutionary outcomes. First, I will talk about environments we developed. Before explaining our contributions, let me briefly introduce EvoGym, the soft robot simulation engine we use as the basis for our multi-agent environments. In EvoGym, robots are constructed in two-dimensional space by combining voxels. Voxels can be of four types: soft voxels, rigid voxel, horizontal actuators, and vertical actuators. Robots act by expanding and contracting the actuators based on sensor information. Examples of sensor information include the velocities and rotation angles of the robot itself and other objects, and the coordinate information of the robot voxel vertices and the distance to other objects. On the screen, you can see the 5 benchmark environments we developed. In this presentation, I will focus on 3 of them. These environments are symmetric in that both robots share the same objectives. In sumo, each robot tries to push the opponent off the stage. As rewards, the robot is given the distance it has moved forward, along with a bonus for pushing the opponent off the stage, and a penalty if it is pushed off instead. In a Wolf box push, the goal is to push a box placed on a platform into the opponent's territory. As rewards, we provide the distance by which the box is pushed along with a small auxiliary reward for approaching the box in order to encourage exploration. In addition, a bonus or penalty is given depending on whether the task is successfully completed. Chimney Crash, in contrast, is an asymmetric environment. The bottom robot must push the top robot upwards, while the top robot must brace itself to avoid being pushed. For the bottom robot, the reward consists of the distance it pushes the top robot upwards, plus an auxiliary reward based on how much it approaches the top robot. For the top robot, the reward is given as the pushed up distance multiplied by -1, penalizing being lifted. So, how can we optimize the body and the control of robots in such competitive multi-agent environments? Let's now take a look at our proposed algorithm. Our simple proposed method co-evolves two populations through 4 iterative processes. First process in the learning phase, robots from the two populations are randomly matched, and each pair learns control policies through competition. The details of the control optimization algorithm will be explained in the later slide. Next, fitness of all robots is evaluated. The fitness of one robot is calculated by averaging competition outcomes against all robots from the opposing population. During natural selection, robots with higher fitness survive while others are eliminated. Finally, in the reproduction phase, the surviving robots are mutated to replace the eliminated individuals, thereby updating the population. Now, let's move back on the details of the learning phase. In the learning phase, robots optimize their control policies through competition in pairs. But how exactly should we apply reinforcement learning algorithms to each pair? The most naive approach would be to continuously train against the latest version of the opponent. For instance, suppose a robot A is currently training against robot B's initial policy. After some time, robot B takes its turns to train, and now its opponent is the latest policy of robot A. Then, after training progresses a little bit, robot A trains again, this time against the latest policy of robot B. These operations are then repeated continuously. However, this approach cannot ensure that both robots learn effectively. If there is a performance gap early in the training, it's difficult to overcome it, and the difference between two robots tends to widen over time. A solution to this problem is a technique called opponent sampling. Proposed by Bansal and his colleagues, this method trains robots by matching them against past opponents rather than only the most recent one. For example, when robot B is in training, its opponent is randomly sampled from an archive of robot A's past policies, ranging from early to current versions. Once robot B's training progresses, the roles are reversed. Robot A trains against randomly sampled policies from robot B's archive. By repeating these processes, both robots are able to learn in a balanced manner. However, care must be taken to avoid situations where only early-stage opponents are repeatedly selected. Now, let's take a look at the robot evolution experiments we conducted and their results. We ran experiments across 5 environments with 3 runs each. Hyperparameters were chosen based on a baseline algorithm from the original paper. Robot size was set to 5 times 5, each population size was 25, and the number of generations was 15. First, we plotted the transition of fitness. Since we ran 3 trials in each of the 5 environments, there are 15 graphs shown here. In each graph, the 2 straight lines represent the fitness transition of the best robot in each population. However, interpreting these fitness plots requires caution. In some runs, it may appear that performance declines over time. But fitness here is a relative evaluation against the opponent's population of that generation. This means the fitness transition alone cannot quantitatively evaluate the robot performance transition. To address this problem, we defined a new performance metric. The performance of a robot is evaluated by averaging competition results against the top 3 robots across all generations and all trials. This formula evaluates the performance of a robot R. The part highlighted in red represents the rewards that are obtained by competing against an opponent robot R-. As highlighted in blue, R- is one of the top 3 robots in generation G of trial T. Here, T ranges over all trials and G over all generations, and the final value is obtained by averaging across them. In this way, we can objectively evaluate robot performance while suppressing the influence of specific trials or generations. The graph below shows the transition of robot performance plotted using this evaluation metric. The shaded regions correspond to the error range. From the graph, we can see that although the trend is not strictly monotonic, the robot's performance clearly shows an overall upward tendency. Let's look at qualitative analysis of robot evolution. In the figure of the upper right, we see robots optimized in the small environments across 3 runs. In most trials, robots acquired front legs highlighted in red and rear legs highlighted in green. By watching the video below, we can see that the front legs are effective for kicking the opponent, while the rear legs are effective for kicking the ground. It's also interesting to note that by concentrating actuators on the rear legs, the robot is capable of generating strong propulsion force. In a valve box push, robots evolved protruding structures on their upper body, highlighted in red, which were effective for pushing the box. Many also developed numerous vertical actuators, making it easier to contact with the elevated box. In the symmetric chimney crash environment, robots evolved distinct structures depending on their role. The top robots evolved structures suitable for hooking onto the wall, highlighted in red, to absorb impact, while bottom robots employed multiple vertical actuators to make contact with the top robots. Some also evolved stair-like outlines, highlighted in green, allowing them to avoid obstacles supporting the top robot. But is competition truly necessary for the evolution of multi-agent robots? This became one of our major concerns. For example, in Sumo, we questioned if a simpler task, like a single robot just pushing a box, would be sufficient. To address this, we conducted additional experiments. We created a dummy environment in which one of the robots was replaced by a stationary box and applied existing single-agent evolution method. Robots evolved without competition in dummy environments were then pitted against robots evolved in the original competitive environments. We averaged the rewards across matches and the results were clear. Robots evolved in the dummy environments were consistently overwhelmed by those evolved in the original environment. The videos here show actual match examples with dummy evolved robots on the left and competitively evolved robots on the right. We also compare the morphologies. In Sumo, for instance, robots evolved in the original environment consistently developed both front and rear legs, while these structures were absent in robots evolved in dummy environment. This finding indicates that the inter-robot competition directly influences not only control optimization, but also the evolution of body. Finally, I would like to conclude this presentation. As a future work, instead of relying solely on free decentralized learning, we could incorporate state-of-the-art multi-agent reinforcement learning techniques. Likewise, rather than training controllers only in fixed pairs, it may be beneficial to ensure balanced training against a variety of robots. Yeah. That's all. Thank you for your listening.
Any questions? Yes. I think you need to come down.
great work, and I liked your presentation a lot. You mentioned with your opponent sampling approach to balancing the pressure on the agent, that you have to be careful not to sample the more recent strategies and keep a kind of good sampling strategy across opponents. Is there a trick for that? And during evolution, the problem of disengagement kind of varies. Sometimes it's a really strong problem because one player has an advantage and can beat the other one a lot. But sometimes that problem is not such a strong problem, and you could let them just fight. So do you have any thoughts about the fact that that disengagement challenge is not a constant problem?
So you mean in our purpose algorithm, the train is done by the training is done in each pair. So
I think it was the scheme. I think it was called opponent sampling.
Opponent sampling.
Yeah.
Sampling. Okay. Could you go over it again? The question?
Sure. So the opponent sampling approach, I think, is designed to fix a problem where one of your agents is better than the other one and just keeps winning. And so there isn't much selection pressure anymore. But that happens at some points in evolution, but at other points, that is not a problem. So it's not a kind of, the opponent sampling strategy is not needed all the time through evolution. Do you have that sense?
But without opponent sampling, the robots didn't evolve successfully. And the opponent sampling is necessary for the training phase. So if we don't apply the opponent sampling like this video, the one robot successfully evolves these structures, evolves its controller, but the other robot cannot train this controller. So in the training phase, I think the opponent sampling method is needed.
Okay, thank you.
Thank you.
Any other questions? Yes.
In the last section there, you compared it to the training against just the block, and then competed that against the ones that had competed against each other.
Based against a stationary box.
So, and your lesson there was that the competition was what made the difference and so on. But of course, whether you have success or not is always relative to a particular task. And in this case, they had different tasks, right? In one case, they're competing against another robot. In this one, they're competing against just the block. So to make a parallel case, did you do one where you had two ones that were trained against a block and then competed against each other?
So you mean in my ablation study, this match is one from the competition and one is from competition against station works. And you mean the
without competition?
Is that the competition?
So you have with competition, so they're trained against each other. And then here's without competition, the dummy is trained against the block. So my question is, in the without competition, if it's dummy versus block and the other is trained dummy versus block, then they are trained, then they're competing against each other? Is that the scenario?
We don't run experiments in such situations. But in our feature research, I also think it is also important to simulate such situation.
Thank you.
Thank you.
Okay. Time is over, so thank you so much.
Thank you.
Is there any? Okay. Yes, please. Okay, next speaker is Kishan, Reddy.
No, it's Santu.
Oh, sorry. Then, okay.
Let's go.
And their presentation title is COGENT, Co-Design of Robots with Generative Flow Networks. And then you are, okay, please start.
Okay, good morning. And the first author actually set the scene of this co-design of robots. So I'll be just talking about our work, which is different on two major aspects. So one is it's not an evolutionary algorithm, and it's a single agent. So we'll see how it goes. So we call it COGENT. It's work by my PhD student Kishan, who unfortunately could not be here due to his work commitments, and along with other collaborators. So this shows the several common types of robots that we have around us today. But if you look at them, they are mostly inspired by the human form or the kind of uh, creatures or the uh, tools that we use in our daily task. So these robots are very good at what we also can do well. But what about the tasks that we humans can't do really well, where we really need the robots, right? So that's the kind of motivation of our looking at robot design again and again. So if you look at the nature has done a fantastic job of coming up with exotic designs for different kind of tasks, but the nature has got millions of years of evolution to come up with these kind of designs. We don't have millions of years. So in this work, we look at like how we can design similarly exotic configuration of robots for very, very specific kind of task. Uh, of course, without needing the equivalent of millions of years of evolution or computations. So I think the previous author has already talked about this core design, which is a kind of a bi-level optimization problem. The way we describe it is like, okay, we have got this generator at the top level, whose job is to produce designs or generate robot designs. And then bottom level, we have got the control optimization, the learning problem, which is the job of the evaluator to learn the control policy for that given design, and then the evaluate that design on the suitability of a given task, right? So these two like work in a loop. So the control optimization evaluates the designs from the design generators, gives the feedback to the design generator learns from that feedback, and produces the better design. So they work in this kind of loop. But as you can see, the both of them, the it's very demanding computationally. And the generator and the control optimization, the evaluator, they both need to be very, very capable. And then if you want to really make them efficient, what you want is that design generator to be very quick learner, but capable of learning all the the nuance of the designs. And where the evaluator, we want them to be reliable, so that they train and they test properly, but we also want them to be fast. And in machine learning or any kind of learning, we know demanding something to be capable and also the fast is kind of at odds to each other. So this works look at the best trade-off that we can have in this kind of scenario. Of course, it will be the related work looks at some of the evolutionary co-design that the audience here would be most familiar with. That dates back to Carl Sims' work in 1994, which shows that you can co-evolve body and the brain together to come up with very adaptable behaviors. And then starting from there, researchers have looked at like how to expand from that basic tenet So one of the things that we'll be presenting in our work is that, okay, how can I come up with the diverse solutions at one training run? So some of that aspect has been addressed in the evolutionary domain to quality diversity, that kind of framework. Uh, but the basic issue with the evolutionary approach, as the way I see it, is it very, very computational demanding. It takes a lot of iterations to come up with uh, when you start to come up with the good designs in the populations. Of course, researchers try to address them with some kind of the efficiency tricks like early stopping and some other things, but that way again I see it, they still remained very, very computationally expensive. So the new framework that is coming up, like I guess like the last 10 years, with the advent of graph neural network and the scalability of deep reinforcement learning. So so researchers have come up with combining them both in a single decision-making process. So instead of like treating them different, so we got like say graph neural network and the policy learning put together and then train end to end to come up with the design and its control mechanism at one go. So the robots that we are trying to design, so that can be represented as a graph. And then that reinforcement learning is used to optimize both the body and the control policy at the same time. Here, of course, the efficiency issue comes again, because as you can solve simple design problem, people looks at the more complex problems, and then the researcher came up with some ideas like symmetric paths. Robots, they tend to be symmetric, or other kind of tricks to make it sample efficient. But one of the key drawback of the current version of this RL-based design mechanism is that they still look for the single-based design. So if you want to see like, okay, are there like a diverse kind of designs that are equally good for the given task, you probably have to rerun it with a different initialization. So introduce randomness at the beginning so that it kind of goes to a different solutions. So that's the kind of problem again that we are trying to solve. Use the deep RL-based method, but come up with something that can give you like a capacity to generate diverse solutions at one go. And that takes us to GFlow nets. GFlow nets or generative flow networks are a type of generative model that learns to build graphs step by step. Okay. So the key idea is that the probability of generating a particular graph is proportional to the quality of the reward. So better design the natural sample more often. So if you got a like trained GFlow net, you can continuously keep sampling new and new designs. And the occurrence of the designs are kind of proportional to the kind of reward that brings. So you can generate a lot of like say different kind of robots with good rewards, but you'll also sample some kind of not so good rewards occasionally. So because that's what GFlow is. It's a sampling mechanism from that large discrete space of the graph. So I'm not going into the technical details of like say how it works, but in a nutshell, it's constructed as a flow network, where you have got a source of flow and you've got a sink where all the flow terminates. So the flow needs to be balanced between source and the sink. The total flow is proportional to the reward or the value of that graph. And then each path from source to the sink is kind of given the credit assignment in the way that that path brings value to that total reward that the graph brings. So, so that's the idea. I think I mean, if you look at the GFlow nets and this kind of the uses, they have been used in materials designs or the molecule design where the search space is quite large in terms of like combinatorial space. So we are the first one to look at how we can use it for robot co-design. But we had to need to do some adaptation to make it really work for our case. So this is the whole framework. So this left side is a generator, which is the GFlowNet, and the purple on the top that shows like say the kind of the action space, like okay, which parts to add to the next in the partially completed robots and what to add, and there are other attributes that you can consider during this graph generation process. So GFlowNet's job is to generate the graphs that's in the blue block, and then it goes to the evaluator, where the evaluator job is to train that given robot and then evaluate in a test environment. And when you got the value for that graph or the total reward obtained in the graph in the test environment, we put in the replay buffer, and that replay buffer used to train the GFlowNet. GFlowNet is also trained with the RL optimization, so that's the use of replay buffer there. So, so the kind of key contribution in the evaluator step is that we change the reward function a bit so that it becomes efficient. And we have also done some changes in the way the GFlowNet is trained to, again, to make it learn faster, like to make it a quick learner. So very quickly, the first approach to make the evaluator fast is don't wait till the end of the training to judge whether a robot is a good or not. Look at the like early part of the training to come up with a signal or derive like how steadily it is training. So in that example, you can see that if we have evaluated these two designs based on their total rewards, they would come out as the same. But if you look at their rate of improvement between some fixed period of time points, usually the last half of the training, we can see that the left one had more steady progress than the right one, which is quite unstable. It's just natural to assume that the left one will improve further given more training, right? So the evaluator needs to evaluate it with a very tight training budget. So the full-scale behavior may not have emerged yet. But it's sort of evaluating the running capability of a robot by looking at how fast and steadily it can go from walking to jogging, right? So you can see that, okay, given more training, it will definitely go from jogging to running more steadily. So that's the key. That's one of the key ideas. And the second idea is that when we are designing robots which have got different number of parts and different kind of parts, so there's a spectrum of simple robots with a few parts, and there will be like complex robots with the many parts. So we can't give like say the same kind of training budget to each of them. So that's why like so we come up with the idea that okay, a part is also sampled with this additional training budget that we need to give it to it. So the complex one with many parts can have like a more training budget, or a design which has got very good potential uh, and requires a little bit more training to show, but it will eventually can come up with a very good design. They can also sample like a higher training budget, but the way we kind of enforce that, not simple model does not like simple robots do not like exploit like high training budget to get to like a very good value, uh, is that we penalize. So this is the idea that we penalize the use of extra resources. So that means like say that a robot configuration only samples like say extra resources if that gives like say high marginal benefit to its value or its total reward, given the extra computation that is using. So sort of like our sampling space is not just a design, it's a design times like say the resources. So so at the end of the process, we'll get designs which are complex but also resource efficient to reach to the goal or the task that we want to master. So this is like say putting it all together. We have got this reward for the GFlowNet training, where it's combination of the total reward, but also the combination of these two other rewards that I just presented. I'm not going to the details of the environment because I think they are very common ones, and Ivo Jim already the first author presented. So if you look at the results, so there are baselines, the evolutionary based baselines of the deep RL-based baselines, and then COGENT constantly outperform them on different kind of locomotion tasks. And the COGENT's number is actually the average over 5 designs sampled from the fully trained GFlowNet. So as you can see, like it was able to come up with a good designs, like designs with a good high reward. And I'll also show you that the designs are also diverse enough. They're not like the same designs again and again. So these are some of the designs that it has come up with. So for the EvoGym, we have done like 4x4. And then this is the bottom task is the bridge walkers, where this bridge is oblique and then it needs to like just cross it. As you can see that the designs are actually quite different. So these are again like the way that they are working. As you can see, it's not just the designs are different, their control mechanism also like different. So the idea is that you can train at one go and you can come up with like a diverse set of designs from that same training run. And then there are like say ways you can improve the efficiency of the training run is the core of what I'm presenting today. Simple ablation, like with or without this, the contribution of rate-based prioritization or the cost hour sampling. As you can see that they both are an important part of that. So in essence, like we presented COGENT, which is a novel co-design method using GFlowNet. So we presented some of the key techniques to make them efficient. In a future work, we try to look at like say how we can make it efficient further by exploring synergy between the robots that have been generated across the different iteration of GFlowNet. So that's about it. Thank you very much.
Any questions? Nobody? Any comments? Oh, please. Down to.
Great talk, thank you. Nature uses bisymmetry. Have you considered a way, working with a 2D framework, it's very difficult to create bisymmetry. Have you considered any possible way of running parallel applications that they can then come together as a bisymmetric creation post-training where you have the same results so that you have more of a natural design as a result? Not sure if I'm being clear in my...
It's an interesting idea. So no, we have not considered that, but definitely there's something worth considering. Thank you.
Any other questions? No one? I just want to know, I think I missed the point, but there is the hardware design and also the learning of the new controllers, right? And then how do you deal with that time scale differences? I mean, usually to train the controller, you should use the fixed body structure. But how do you?
No, that's how we do, like say, so that when GFlowNet constructs a graph, it does it by step, but there is a like starting point and the terminal point. So that means like say it goes constructing the graph and then it ends. And then you got the graph and this graph is translated to the robot.
Yep.
And then we train that robot. So it's kind of like separated process. Then when the robot's trained, then it gets the feedback and the GFlowNet gets trained.
So you need to adjust the time scales.
Yeah.
Okay. Thanks. Any other question? And then, okay, thank you so much.
Thank you.
Okay, next speaker is Henry Hickson, and their presentation title is Back to Bee-sics, Learning Information Sharing Strategies for Robot Swarms Through the Hive. Okay. Whenever you are ready. Okay, please.
Cool. Hi, everyone. My name's Henry, and I'm here as part of the Bristol Robotics Lab and the Swarm team, which is run by Professor Sabine Howitt. I'm really grateful to be here, and I think it's really cool that we can all come to Japan and sit in a room and talk about robots. It's very exciting. So I'm here to talk about my paper called Back to Bee-sics, and this is all about learning information strategies, specifically in robot swarms. So my personal passion is about getting robots out into the real world. And my goal is to use robots for real world impact. And so the vision that's kind of led to all of this work in my PhD is this interconnected system of all kinds of devices. So what I'd love to see in the future is a system where we can have robots, humans, IoT devices all working seamlessly with one another. And this bit of work is my very small contribution towards that greater vision. So as I think a lot of people in this room will know, there's kind of two major methods of controlling multiple robots. We have the distributed method, where every robot makes its own decisions on board. Then we have the centralized method, where we have essentially a single controller, which is telling every robot what action to take at any given time. These both have advantages and disadvantages. But what we want to do with this work is look at something in between. And there's lots of hybrid paradigms, but the one that we're shooting for is a system that is based on a completely distributed swarm. So every robot here has its own agency and makes its own decisions. But we also allow them access to a shared centralized knowledge base. This is stored off-board and allows them to communicate and send information via a central source, but not be controlled by it. And what we want to do here is kind of shift the existing swarm robotics, which have heaps of advantages in terms of reliability and scalability, but make them more deployable. And if you look at robots, multi-robot systems in particular that are deployed in the real world right now, they're often in this centralized camp. So we think if we can get something somewhere between the two, we might be able to get our swarm robots out there and doing real world tasks. So the inspiration from this came somewhat from bees. And if there's any bee experts in here, I have to apologize because this is probably not 100% biologically accurate, but it's inspired by. And what bees do, which I think is really cool, is they all go out and they make their own decisions, right? They have their own agency. They go out into the world and they act based on the inputs and the sensors that they can accrue. But they come back to a single location to share information amongst the colony. They come back to the beehive, and that's how they collaborate information in one single place. And for those that you have looked into this, they do it via this really cool kind of like waggle dance way. So if you haven't looked at that, go and look it up because it's really fun. But the inspiration here is the fact that they come back to a single location to share information globally. And so we thought that bees are kind of a typical swarm, and yet they have this centralized information sharing mechanism. And so we thought we could deploy something similar on robots. So our hybrid architecture looks something like this. We have a lower layer, which we call layer 0, and this is a typical distributed swarm system. So here, every robot makes its own decision. Every robot has essentially a behavior tree on board. It takes inputs, and it uses that behavioral module to decide what its next actions will be. We then add this second layer, the layer 1, and this is the collective knowledge base. So we design our algorithms and our controllers on the robots so that the system can work completely without the knowledge base. If the knowledge base falls down for any reason, the robots will still operate. But if they have access and if they have connectivity to the system, they can use it to coordinate. We formalized this in a piece of work that we called the Hive. And so this is a formalized architecture that basically pulls all of this together. And here we have both humans and robots involved. So the start of this is that the human collaborators would upload tasks into this Hive system, which, as I said, is typically stored off-board, for example, in the cloud. We then have the robots, which will update and provide their observations. So this is anything that they can sense or infer from their onboard sensor suite and from the environment. And then we do some fun processing inside the Hive, which creates what we call the Hive knowledge graph. And this is a graph-based representation of all the information that is relevant to a specific task. And that's the key, that we do some Hive-level processing that means that the information stored in the Hive is relevant to one specific task. And I'll explain that a bit further. To generalize the Hive itself and make sure that it's possible to use that on a range of different tasks and robots, we define a few kind of standard information types which make up the nodes in that knowledge graph. So we have entities, these are all fixed items. We have tasks, which again are the things that are defined by the humans. And then we have the information, which is the interesting one. And this is dynamic data that can change throughout the task. A key thing to note about the information is it has a weight value. And the weight value is what determines whether or not it gets included in that final knowledge graph that is used for the task. So we can switch bits of information on or off to decide whether or not we want to include them in our knowledge graph for that task. And that's important for a number of reasons, which again, I will come on to. So in the end, we have this system where each robot has some observations, they share it, and they can communicate centrally, but still make decisions locally. And this works pretty well. I wanted to include a video of real robots because we're in the robot session. I feel like we had to have some robots in here. This is slightly different to the task I used in this paper, but what it shows is that by sharing information, we're able to essentially complete tasks fairly efficiently. And in this task, it's all about delivering items. And we showed that compared to not sharing information globally, we can see some really nice performance increases. But the point of this work, and this paper in particular, is based on the actual information selection. So what information gets shared? And there's two major challenges towards this. The first one is that we have to select information that is maximally beneficial for a given swarm, for a given task, and for a given environmental configuration. And so some of the previous work we did showed that if you choose the incorrect information and share that globally, you can actually cause a decrease in performance. So that was quite counterintuitive, but interesting. And that comes from things like if you have noisy sensors and you're sharing information which detracts from the system, or even sometimes if you share information that intuitively works really well at a small swarm size and you scale that up to a large swarm size, it can kind of mess things up. So we need to make sure that the information we choose is relevant to the task and is going to actually help. And then the second one is related to communication. So we want to minimize the amount of data that is sent so as to not flood the network. Now, because we're using a swarm system which typically is completely distributed and not reliant on any of these centralized infrastructure networks, we want to maintain those really nice properties of redundancy and scalability. But because we're pulling networks into this system now by adding a cloud, we have to then account for that. And one of the major issues with network systems is they're all bandwidth limited. So every communication network that we use, whether it's Wi-Fi or 4G, has a maximum amount of information that it can handle. And if we spam it with all the observations that every robot can take, what we see is quite a fast network degradation. We get latency, we get dropout, and the system falls down again. So we have to manage sharing information that's going to help, but also not sharing too much information that we break the system down. So if we go back to the architecture again, the key part of this system that allows us to do that is this weight optimization. And in here, again, if you remember when I was talking about the information part of the system, we have a weight for each piece of information. And centrally in the cloud server itself, in the Hive, we can set those weights based on the information and based on the task. So if you imagine at the start of a system, it's a completely blank slate. Ideally, this is generalizable, so it works for any task, any set of robots. So we have a blank slate, the humans come in and we give a task to our robot systems. The robots, which can be, again, any type, can come in and tell us what information they can share. And then the cloud does some optimization without any actual prior knowledge of the task itself or the robots. We can optimize a set of information that is useful for that given task. The other thing to point out here that is really nice is that we can tweak the information online and essentially change the behavior of the swarm without actually reprogramming the robots explicitly. So we can use information as a method to add some level of control to the system without the really computationally heavy learning processes that we see in other works. So we tested this learning method with a distribution task. In this one, it's based on our DOTS robots, which I showed before. And the aim here is to move essentially from one task to another, T1 to T2, via 2 doors. So it's kind of like a really basic traffic scenario. And the aim is that we have to move between that 100 times. So we can imagine we're moving things from A to B or something similar. We gave the robots an observation space, again, based on the real robots themselves. So on our real robots, we have a robot operating system, which many of you may be familiar with, which has a certain amount of information about themselves that they know, observations. So we gave these observations to the evolutionary algorithm to allow it to essentially select from that subset. And they include things like the position, the speed, the heading, the task status, anything that the robot can infer whilst operating. And then we run a agentic algorithm on this to essentially demonstrate that we can train the system. There's two key parts of the fitness function. It's actually a fairly simple setup to run, but it's those two challenges that I mentioned before. So we have the performance, so maximizing the time at which we complete that task. And then we also have a cost for communication. And here we used a really simple one. Again, we're trying to keep everything super generalizable. So ideally, you can move these fitness functions to other tasks. And the cost here is simply the number of messages that is sent. So we're not doing specific bandwidth calculations. We're just minimizing total number of messages sent. And again, this worked pretty well. Let me get these both playing at the same time. So without the Hive, in this task, what you get is quite a messy scenario. So the robots are randomly choosing a door to move between for each scenario. And essentially, this causes lots of traffic buildup at the doors. And then on the Hive side, what the robots chose to share in the end were two things. One was heading and one was position. So the robots essentially predict how much traffic there is at any given door, and they make a decision whether to carry on going for that door or go to the other one. And the nice thing about this is we got this really awesome emergent kind of diamond shape forming, which was not explicitly programmed at all. That just came out and emerged from the ability to share extra information globally. When the robots are operating locally alone, they can sense a level of traffic, but only within a much smaller radius. In terms of the kind of performance of this, everything converges fairly nicely. The other nice thing we realized about this task, which we started off running the task, I think, 10 times and taking averages, and then we took it down and down and down. We realized we could actually converge just as well by running the task once, which was nice. I think that will vary with different tasks, but this one was very receptive to being run a single time. We also compared this performance-wise to some baselines. So we had the no sharing, which is the purple. We outperformed that pretty well in almost all robot numbers. At 200, the task is over very quickly, so there's less of a distinction there. We also compared it to two other baselines. So one is a fully centralized system. So this is a multi-agent path planning algorithm that optimizes this to the maximum that can be. And we were happy that we were reasonably competitive at this, especially from 50 robots and above with a Hive system. And then we also compared it to a naive sharing mechanism, and this is where the robots can share everything. So this is just to check that we have selected the optimum information to share for this task. And as you can see, we match that performance as well. And the key thing compared to the naive side is that our bandwidth, or the throughput, the amount of messages that are being sent per second, is significantly decreased. So our reliance on that network and the likelihood of our getting network discrepancies from this system is significantly reduced compared to just blanket sharing everything. And that's one of the major benefits of evolving this and selecting information a bit more selectively. So we're really happy with the results for this, and I think the overall architecture, again, has proven itself in lots of instances. We have a few things we'd like to work on next. One of the downsides of this system is that we have quite a limited observation space, and so we think there's some optimization and some improvements we can make within the whole system that allow us to explore a broader area, a broader state space. We're also looking at the distributed side. I often get the question when I present this work of why not do it distributed. It does work distributed, but one of the things we're really interested in pushing is whether we can use these infrastructure networks. We have amazing Wi-Fi and 4G and 5G all around us, whether we can make use of those and still maintain our positive properties of the swarm. So there is potential to do distributed work, but we are trying to push this message of what if we use these other methods, this other technology available to us, especially for real-world deployments. And of course, we're always pushing for real-world robotics. And again, that's a massive passion of mine, is to get things out there into the real world. And we are currently exploring lots of things with this, both with our DOTS robots and with other ideas, startups, and other things. So I'd be very happy to chat about things like that as well, if anyone's interested. So yeah, that's me. There's a QR code for my contacts if everyone wants to reach out and continue the discussion. But I'd be happy to take questions too. Thanks.
Okay, any question? Please come down to the mic, please.
This might be a naive question, but I'm not sure if I understood if this was something you were doing or not. Do you allow the bots in the swarm to differentiate themselves from the other bots? So like to take on lead roles and things like that?
Yeah, no, it's a good question. At the moment, everything we're running is completely homogeneous. So every robot is essentially equal to every other robot. In the literature, there's a lot of kind of similar works, I think, that will assign hierarchical roles that can essentially take on that kind of cloud base, right? So it would be interesting, and one distributed option would be to do exactly that. And I think it'd be really cool to do is that have one of the Hive basically stored on a robot, and then have all the other robots communicate with it. So yeah, I think there's a lot of potential there. And I think in that distributed part of that further work, some of that would fit in really nicely. So yeah, it's a great suggestion.
Hey, I think maybe I missed something. What's the policy? What's the architecture of the policy on the robot, and also what's the mechanism for optimizing the message weight computation? I saw you used evolutionary strategies to optimize it, but what are you optimizing?
Yeah, okay, I probably skipped over a couple of those things. Yeah, so the policy on each robot is essentially a behavior tree that we write manually. We're quite keen to, I guess, decouple communication and control, which is part of the point of this. We're not looking to run control policy optimization. We're purely interested in the communication side. So we just designed a kind of a broad behavior tree that takes in inputs from the surroundings and allows the robots to move from point to point. And they do have things like global localization, for example. But that's based directly on our DOTS robots. It would be possible to pre-train a control policy as well and run it in the exact same architecture. So yeah, I skipped over it because I guess the policy isn't necessarily the main point, but it can be applied in any way for control. And the second question was the evolution. So that's what the genetic algorithm does essentially. So we are running that algorithm through the fitness function, and essentially because it's a simulation, we can run one iteration of the task with a selection of weights on those observations that robots are able to share. So for example, we'll pick a random selection. So we might pick robot position and robot speed. We'll run the task. We'll record how quickly the task is completed and how many messages are sent. That gives us the fitness function. And then we will continue iterating that with some of the parameters I showed to converge on a set of informational weights that are best for both performance and communication. So that's the bit that's
Okay, so that's all simulate. So you're simulating it to figure out the weights, and then you're using those weights.
Yeah, exactly. Yeah, and so we worked out that I think because we can run it once, we can run this effectively online in, I think it's like a few hundred runs. So in the real world, it works out about half a day of training. We haven't run it, the optimization on the real world, but yeah, that's essentially. And the other nice thing, I guess I didn't point out, is that we can, because the robots always complete the task, because the control and communication policies are separate, although they might complete it slower when they share some information rather than when they share other information, they generally always complete it. So it's quite a safe system to run online as well. Cool.
Hi, great talk. That was super interesting.
Thanks.
Do you have any data, and if not, maybe any intuition about how a swarm that was optimized without the Hive compares to a swarm that was optimized with the Hive, but then had the Hive knocked out? In the spirit of putting these things in the real world, can they compete with those optimized without the Hive if they're operating with it and then lose it at some point due to an environmental, unseen circumstance?
Yeah, it's a really good question. So yeah, there's another whole bit of work that we've done on networks themselves, and my other supervisor is in the network space, and so we've worked a lot on all sorts of network degradation things, from adding latency to adding dropout and all sorts. Essentially what happens when the system is knocked out completely is we get graceful degradation. So as you lose connectivity, the performance decreases back to the baseline of the swarm with no Hive, but we don't get degradation below that in general. And that's because we've designed the system to work at the baseline first. So that layer 0 that I showed is always an operational swarm system. And then the layer 1, the global information sharing, is kind of like a bonus to that. So it degrades nicely. So one of the experiments we did, for example, was to reduce the number of connected agents from 100% connected down in increments of 10% down to 10. And you get this degradation down to, essentially the baseline. The interesting thing about that as well is that in comparison to a centralized system, which we also tested, the centralized system degrades really badly. So when you start losing connectivity on a centralized system, you get all sorts of havoc and robots completely not working. And so there's a massive advantage compared to the centralized as well. Thanks.
Yeah. Oh, sorry. We are running out of time. So okay. Thank you so much.
Okay. Thanks.
Okay, then the next presentation title is How Perception, Actuation, and Communication Impact the Emergence of Collective Intelligence in Simulated Modular Robots. And this is a journal paper, and then unfortunately they couldn't come to the conference physically. And then the presentation is recorded in advance, and then it's going to be played.
Hello everyone, I'm Francesco Rusin, and I'm here to present you the paper How Perception, Actuation, and Communication Impact on the Emergence of Collective Intelligence in Simulated Modular Robots, which I wrote along with my supervisor, Professor Rick, and which was published in the Artificial Life Journal in 2024. So what are we talking about? We're talking about modular soft robots. So modular robots are robots that are composed of a collection of smaller and simpler parts, which are called the modules, that are pretty limited in their capabilities, but they can achieve pretty complex behaviors by cooperating. This can also be observed in nature, as there are various examples of, in particular, animals in which the individuals themselves are pretty simple and weak, but they can do some pretty complex stuff by cooperating. However, when this happens in nature, we just have to acknowledge that this exists. Instead, when we are building a robot, there are some choices we need to make. There are some parameters we need to optimize. And depending on how we perform this optimization, we may actually end up encouraging more selfish behavior. We may end up with robots that in which the modules perform the task on their own instead of cooperating. And that leads us to our research question, which is which factors impact on the emergence of collective behavior instead of a selfish one. Now, we've distinguished between two macro areas. There are the internal factors, which are the factors related to the modules themselves. Inside these, we've distinguished between perception, which refers to how much information the modules have about the environment. Actuation, which refers to which actions can the modules actually perform, and communication, which refers to how much information do the modules share with each other. And there are also the external factors, which are the factors related to the environment. For this, we have chosen the degree of selfishness we are encouraging with the way we measure performance. So the robots we're using are the single voxel robots. For computational complexity reasons, we are working in 2 dimensions. Theoretically speaking, our results should be portable in 3 dimensions. So our models here are the voxels, which are these soft squares that can contract and expand their sides. And they can also attach to and detach from each other on said sides. Now, we have equipped these voxels with some number of sensors. We used an angle sensor that can detect the current angle between the voxel and the horizon, a contact sensor that can detect whether the voxel is in contact with another body, which would be another voxel or the floor, a side length ratio sensor for each side, which I think is pretty self-explanatory, a side attachment sensor, which for each side detects whether that side is attached to something else or not, and some number of proximity sensors, which detect the distance of the closest body in a given direction. We also equipped the voxels with a communication system. This works this way. So at each time step, each voxel emits a numerical signal from each of its sides. The other voxels, if they are close enough, can detect that signal on the side that the signal actually lands on. In this example, the voxel B detects the write signal from voxel C and the write signal from voxel A on its left side, and it detects the left signal from voxel B on its right side. Voxels A and C do not detect each other's signals because they are too far away. So, and these numerical signals act as additional inputs for the controller. To model our controller, we used a neural network with a fixed structure. So basically, to optimize a controller just means to find the correct parameters. To do so, we used a very standard genetic algorithm with mutation and crossover. We just picked our population, evolved it, and then took the best individual. So the tasks we had our robots perform are piling, in which the voxels need to get as high as they can, and locomotion, in which they have to run to the right as far as they can. We used piling to measure the impact of perception, locomotion to measure the impact of actuation, and to measure the impact of communication. In both cases, we have considered voxels that were able to perform intervoxel communication and voxels that could not. Now, let's start from piling. I remind you the way we measure our fitness is actually a way to define how much we are encouraging selfishness. So we have considered 3 fitness functions. The full max fitness function is the max height averaged during the simulation. This is the most selfish because only one voxel matters and only 1 second. So the voxels are encouraged to like climb on each other and be selfish, let's say. Then we have the max average, which is the average of the maximum height during simulation. This is still selfish because only the maximum matters, but it is a bit less selfish than the full max because we expect the voxels to cooperate to form a stable structure. And finally, we have the least selfish of the fitness functions, which is full average, which is the average height overall. This is, of course, very selfless because every voxel has the same weight. Now, to measure the impact of perception, we consider voxels with different number of proximity sensors. We consider 4, 8, and 16 sensors. Of course, the more sensors a voxel has, the better its perception. Now, these are the numerical results. Here in red, we have the voxels that actually could communicate with each other. In blue, the voxels that could not, sorted by the fitness function and the number of sensors. The first thing we can see from this plot is that communication is not useful, because without communication, we always perform the same or sometimes even better than with communication. This is probably because the voxels perform morphological computation, meaning they can find ways to communicate without explicitly using communication. So communication becomes redundant and it just widens the search space. So of course, wider search space means it's more difficult to find a good solution. A second thing we can notice is that in the 2 more selfish cases, the extra perception is useful. Instead, in the most selfless one, this is not the case. I can show you why. So this is a robot optimized with the overall maximum. You can see they climb on each other very high and then they collapse down. They have no reason to actually stay high or cooperate in any way which is not climbing each other, because only the overall maximum matters. Instead, these are voxels optimized with the average of the maximum. You can see they don't get as high, but they manage to be stable. And finally, these are voxels optimized with the overall average. You can see here they don't even try to get high, they just push each other up. This also explains why here extra perception is not useful, because they don't need it. this is not a complex behavior, so they don't need the extra awareness. Instead, in the other two cases, there were voxels rolling on each other, which is a fairly complex behavior for these robots, so the extra perception was useful. Now, that sums it up about piling. Let's talk locomotion. As I said, we use locomotion to measure the impact of actuation and also communication and selfishness, but the difference of piling is in the actuation. To do so, we consider two kinds of controllers. We consider a controller that had full power. It could always do everything, contract, expand, touch, detach, and a controller that could only do contraction expansion, but it could not attach and detach. Of course, in this second case, it's not the same to start attached or to start attached because you cannot change. So we consider these two cases separately. Now, again, the fitness function is the way we measure the selfishness encouragement. So we chose two fitness functions. We consider the velocity of the fastest voxel, which is the most selfish one because only one voxel matters. And then we consider the average velocity between the voxels, which of course is more cooperative. Again, these are the results. Again, communication is not useful, probably same reasons before, morphological computation. But other than that, there's not really much information we can extract from these box plots. But we can extract a little bit of information from the videos. These are voxels with full control optimized for the average velocity. You can see they cooperate a lot. And also they are using the full control because on the bottom line, they are constantly attaching and detaching. So it's not like, yeah, they have full control, but they wouldn't need it. They are actually using it. Instead, these are voxels that could not attach, optimized with the maximum. You can see this behavior is very different. Only one voxel runs, the others don't. Now, I remind you, all these voxels have the same neural network, but this one runs and these don't. This is probably because this one is flipped. So the evolution found a way to flip one voxel, so these ones stay still because they are not needed for the performance, because if this runs faster, what these do is not important. So the evolution does not favor a behavior where the others run. The evolution favors the behavior when one gets flipped and runs, because that's everything that matters to the evolution itself. So let's wrap this up. So what did we find out? Well, first, if a task encourages the robots to be selfish, the robots will be selfish. This turned out to be the most important factor. Second, the internal factors do have an influence on the behavior. They may not have an influence on the performance. Sometimes they do, sometimes they don't, but they do impact the behavior. And finally, communication is not beneficial. Probably this is because it's redundant, but with what we know for a fact is that, at least in this case with these robots, communication is not beneficial. That wraps this up. Yeah, that's it.
Okay, then this is the end of this session, and thank you for coming. And let's thank for all the speakers. Thanks so much.